Alex, have you seen the headlines lately? It feels like every other day there's some new astronomical discovery, but this one really caught my eye and honestly sent a little shiver down my spine.
Oh, I definitely saw that one pop up in my feed. Maya, it's certainly designed to grab attention, isn't it? The phrasing, heading our way, immediately conjures up images of Hollywood disaster movies, even if the reality is usually far less dramatic. But it's true, there's been a massive influx of new celestial body discoveries recently, and it's all thanks to some truly incredible new technology.
Exactly, and that's precisely why I wanted us to dive into it for things I know nothing about. Because while the headline is dramatic, the actual science behind it is even more fascinating and, dare I say, reassuring in many ways. It's not just about a sudden appearance of new threats, but about a revolutionary leap in our ability to see what's actually out there in our solar system, which is a game changer for planetary defense.
You're absolutely right. It's a prime example of how scientific advancement allows us to better understand our cosmic neighborhood, not necessarily to panic, but to be better prepared. So, let's start with the star of the show here, the Vera C. Rubin Observatory. This isn't just any old telescope, is it? It's a whole new level of sky scanning power. What makes it so special, and why is it located where it is?
It really is something out of a science fiction novel, Alex. The Vera C. Rubin Observatory, located high up in the Chilean Andes, is a truly monumental achievement in astronomy. Its primary mission is the Legacy Survey of Space and Time, or LSST, which is essentially a decade-long project to map the entire southern sky repeatedly. This isn't just about taking pretty pictures, it's about detecting changes, movements, and incredibly faint objects that we've never been able to see before with such detail and speed. The clear, dark skies of the Atacama Desert in Chile provide the perfect, unobstructed view for this kind of rigorous astronomical observation.
A decade long project to map the entire southern sky. That's an incredible undertaking, and I understand it houses the Simone Survey Telescope, which itself is equipped with the world's largest digital camera. We're talking about a camera capable of capturing 3.2 gigapixels images, which is just mind boggling when you think about the amount of data it must be collecting every single night. How does that kind of power translate into finding objects like these asteroids, which are often small and moving incredibly fast across the sky?
That's where the magic truly happens. Alex. The observatory's 8.4-meter mirror is huge, allowing it to collect an immense amount of light, but it's the combination with that colossal digital camera that creates this unprecedented capability. The camera images a vast patch of sky roughly equivalent to 40 full moons in a single exposure. Then the telescope can reposition itself and take another image just seconds later. It's designed to scan the entire visible southern sky every few nights, creating a time-lapse movie of the universe. This repeated imaging is absolutely crucial for detecting faint, fast-moving objects because astronomers can compare images taken at different times and spot anything that has moved or changed in brightness. It's like having an incredibly sensitive wide-angle motion detector for the cosmos.
So it's not just about seeing further, but about seeing faster and broader, which is key for tracking dynamic objects in our solar system. The sheer volume of data must be astronomical, pun intended. It's designed to detect change, and obviously an asteroid moving across the background of distant stars is a very significant change, and it's only just begun its operations, right? The discoveries we're talking about today are from its preliminary data, not even its full operational capacity.
That's precisely it. The Rubin Observatory officially began its new surveys in mid-2025, and these initial discoveries we're discussing are from early optimization surveys. So what we're seeing is truly just a sneak peek, a tip of the iceberg as many scientists are calling it, of what this incredible instrument is capable of. It's like testing out a brand new supercomputer with a relatively small task and still getting mind-blowing results, hinting at its full potential for the future. The sheer volume of data it's already generating is pushing the boundaries of what's possible in astronomical data processing.
And what a sneak peek it is, let's get to the numbers that really caught people's attention. Over 11,000 new asteroids discovered in its preliminary data alone. That's a staggering figure. Can you put that into perspective for us? How does that compare to previous discovery rates, and what does it tell us about the asteroid belt that we didn't know before?
It's absolutely monumental, Alex. To give you some context, This single batch of over 11,000 new asteroids represents the largest submission of asteroid discoveries to the International Astronomical Union's Minor Planet Center in the past year. That means in just a short period of preliminary testing, Rubin has contributed more new asteroid data than many other observatories combined in a much longer time frame. It really underscores the unprecedented depth and speed of its scanning capabilities. What it tells us is that our current catalog of asteroids, while extensive, is still far from complete, especially for the smaller, fainter objects. The solar system is a much busier place than we previously thought, and Rubin is finally giving us the tools to properly inventory it.
And among those 11,000, the ones that really made headlines were the 33 near Earth objects, or NEOs. This is where the heading our way part of the headline comes in. Can you explain what exactly defines a near Earth object and why these 33 are of particular interest, even if they aren't an immediate threat?
Absolutely, a near-Earth object, or NEO, is defined as an asteroid or comet whose orbit brings it within 1.3 times the Earth-Sun distance. To put that into perspective, 1.3 astronomical units, or AU, is about 120 million miles. While that sounds like a massive distance in astronomical terms, it's considered relatively close. The reason these 33 newly identified NEOs are so interesting is precisely because they are in our cosmic neighborhood. The more we know about objects orbiting near Earth, the better we can understand potential risks and track their trajectories over long periods. While none of these 33 pose an immediate threat, their discovery significantly enhances our catalog of objects we need to keep an eye on, improving our long-term planetary defense strategy. It's like finding a few more pebbles on a path you walk every day. You want to know they're there, even if they're not currently in your way.
That's a great analogy, Maya. It's about comprehensive mapping and understanding, not just reacting to immediate danger. And it wasn't just asteroids and EOs, right? The Rubin Observatory also identified a significant number of trans-Neptunian objects, or TNOs, which are even further out in our solar system. What can you tell us about those and why their discovery is also important, even though they're not heading our way in the same sense?
That's right, Alex. The observatory identified approximately 380 new trans-Neptunian objects. These are icy bodies that orbit beyond Neptune, in regions like the Kuiper Belt. While they don't pose a threat to Earth, their discovery is incredibly valuable for understanding the outer reaches of our solar system, its formation and evolution. Among these, two TNOs, designated 2025 LS2 and 2025 Mexith 348, are particularly noteworthy because they have extremely large and elongated orbits, reaching distances roughly 1,000 times farther from the Sun than Earth. This places them among the 30 most distant minor planets known. Discovering these distant objects helps us piece together the history of our solar system and potentially even find evidence of a hypothetical Planet 9 or other large unseen bodies that might be influencing the orbits of these distant icy worlds. It's like finding ancient, well-preserved artifacts in a remote archaeological dig, offering clues to a past we can only imagine.
So, these initial discoveries, while impressive, are truly just the beginning. Scientists are calling this the tip of the iceberg. What are the projections for future discoveries once the Rubin Observatory is in full operation, running its decade-long legacy survey of space and time? We're talking about a potential revolution in our understanding of the solar system, aren't we?
Absolutely, Alex. Revolution is not too strong a word here. Once the Rubin Observatory is in full swing, it's projected to discover this many asteroids, meaning over 11,000 every 2 to 3 nights in its early years. Think about that for a moment. What took months in preliminary surveys will soon happen almost daily. Over its 10-year operational lifespan, it's expected to ultimately triple the number of known asteroids in our solar system. And for TNOs, those distant icy bodies, the number of known objects is anticipated to increase by nearly an order of magnitude. This level of comprehensive cataloging is truly unprecedented and will provide astronomers with an incredibly rich data set to study everything from planetary formation to the dynamics of our solar system. It's like suddenly being handed a complete, detailed map of a territory where you only had a rough sketch before.
Tripling the number of known asteroids and increasing TNOs by an order of magnitude, that's an incredible amount of new information. Beyond just knowing more, what's the practical impact of this deluge of data, especially when it comes to something as critical as planetary defense? How does Rubin's capability specifically enhance our ability to protect Earth from potential impacts?
This is where the Rubin Observatory truly shines for planetary defense, Alex. Its ability to provide early detection and continuous monitoring of objects is going to be absolutely crucial. With its wide field of view and rapid scanning, it can spot faint objects much sooner and track their trajectories with greater precision than previous instruments. This early warning system is vital. It's anticipated to uncover an additional nearly 90,000 new NEOs over its operational lifetime. Some of these undoubtedly will be potentially hazardous asteroids or PHAs, meaning they are large enough and come close enough to Earth to warrant close attention. By knowing about these objects well in advance, we gain decades, even centuries, to track them, refine their orbits, and if necessary, develop and deploy mitigation strategies rather than being caught off guard by a last-minute discovery. It provides us with the precious commodity of time.
That makes perfect sense. Time is the ultimate resource when it comes to defending against potential cosmic impacts. So, let's address the elephant in the room that the headlines hinted at. Are any of these newly discovered 33 near Earth objects actually dangerous? Because the phrasing heading our way can be incredibly alarming for the general public.
That's a critical question, Alex, and it's important to be very clear and reassuring. None of the newly discovered 33 near Earth objects pose an immediate threat to Earth. This is something that scientists and planetary defense experts want to emphasize. While they are in orbits that bring them relatively near Earth, none of them are currently on a collision course, nor are they projected to be in the foreseeable future. The phrase heading our way simply refers to their orbital path, not an imminent impact. It's a bit like saying a car on a highway is heading your way if it's traveling in the same general direction, even if it's hundreds of miles away and on a different lane.
That's a crucial distinction, and I'm glad we're clarifying that. So, even though they're not a threat, what are the sizes of these new NEOs we're talking about? Because size, of course, is a huge factor in the potential impact if one were to ever cross paths with us. And what size of asteroid do scientists typically get concerned about?
That's a very good point, Alex. Size absolutely matters when it comes to potential impact events. The largest of these recently found NEOs measures approximately 500 meters, or about 1,600 feet, wide. To give you a sense of scale, that's roughly the height of the Empire State Building or the Eiffel Tower. While an object of that size would certainly cause significant regional devastation if it were to impact Earth, it's important to reiterate that none of these 33 are on a collision course. Scientists generally track objects larger than 140 meters or about 460 feet very closely. An impact from an object of this size could cause significant regional damage, potentially devastating an entire state or a small country, and could have widespread global effects like climate disruption depending on where it hits.
So, 140 meters is kind of the threshold for significant regional damage, and the largest of these new ones is 500 meters. That underscores why identifying and tracking them is so important, even if they're not currently a threat. It's about preparedness. But what about our current understanding of these potentially hazardous objects? Do we have a good grasp on how many are out there, especially in that 140 meter plus category?
Unfortunately, Alex, we don't have as good a grasp as we'd like on that particular size category. Current estimates suggest that only about 40% of these mid-sized NEOs, those larger than 140 meters, have been identified so far. This means there are potentially thousands more out there that we haven't found yet. This is precisely why observatories like Rubin are so vital. They are systematically filling in those gaps in our catalog. While NASA maintains that there are no known asteroids large enough to cause meaningful damage to Earth that are currently on a collision course in the foreseeable future, that statement relies on known asteroids. The goal is to turn no known threats into no threats at all by finding everything.
That's a sobering statistic, only 40% of the potentially dangerous ones identified. It really highlights the immense task ahead and the critical role of these new observatories. So, what happens after Rubin finds a new NEO? It's not just a discovery and then, hooray, another one. Is there a process for tracking, analysis, and verification that goes beyond the initial detection?
Absolutely, Alex. The discovery is just the first step in a very rigorous process. Once Rubin detects a new object, that initial data is immediately shared with the Minor Planet Center, which is the global clearinghouse for observations of small solar system bodies. Other observatories around the world then conduct follow-up observations to confirm the discovery and refine the object's orbit. This is where the global network of astronomers really comes into play. By combining multiple observations from different locations over time, scientists can calculate a much more precise trajectory and predict its path far into the future. It's not just one observatory doing all the work, it's a global collaborative effort to ensure accuracy and continuous monitoring.
That sounds like a robust system, which is reassuring. It's not just one set of eyes, but a global team verifying and tracking. And this continuous monitoring is crucial because asteroid orbits can be perturbed by gravitational forces from planets, right? So, an object that isn't a threat today might, in theory, have its trajectory altered in the distant future.
Exactly. Alex, you've hit on a very important point. Gravitational perturbations, primarily from Jupiter, but also from Venus, Earth, and Mars, can subtly alter an asteroid's orbit over long periods. What appears to be a safe trajectory today might, over hundreds or thousands of years, shift in a way that brings it closer to Earth's orbital path. This is why long-term tracking and continuous recalculation of orbits are so vital. We can't just find an asteroid once and forget about it. It requires persistent vigilance and the ability to detect even the slightest changes in its path. Rubin's repeated sky surveys are perfectly suited for this, allowing us to update orbital models regularly and maintain a highly accurate understanding of where every known object is headed.
So, the Rubin Observatory is giving us the when and the where of potential threats with unprecedented accuracy and lead time. This allows for proactive planetary defense strategies. What kind of strategies are we talking about here if a truly hazardous object were identified with enough lead time? Is it still in the realm of science fiction, or are there concrete plans being developed?
It's definitely moving out of the realm of pure science fiction and into serious engineering and planning, Alex. With sufficient lead time, we're talking decades. Ideally, there are several concepts for asteroid deflection. One of the most promising and extensively studied is the kinetic impactor method, which NASA successfully demonstrated with the DART mission. This involves sending a spacecraft to directly collide with the asteroid, slightly altering its velocity and thus its orbital path over time, nudging it away from Earth. Other ideas include gravity tractors, where a spacecraft hovers near an asteroid using its own gravitational pull to gently tug the asteroid off course. There are even more futuristic concepts like using lasers to ablate material from the asteroid, creating a small thrust. The key is that none of these require blowing up the asteroid. They're all about subtle, long-term nudges, which only work if we have that long lead time that Rubin is designed to provide.
It's fascinating how much thought and engineering is going into these preventative measures. The DART mission was a huge success in proving the kinetic impactor concept. But even with all this incredible technology and planning, there's always the chance that something smaller, something unexpected, could slip through the cracks. What about those smaller, still dangerous, but harder to detect objects?
That's a very valid concern, Alex, and it's a significant challenge for planetary defense. While Rubin excels at finding fainter objects, there's always a limit to what any telescope can see. Smaller asteroids, particularly those that are dark and don't reflect much sunlight, are inherently harder to detect, especially if they approach from the direction of the sun. An object smaller than 140 meters, say 20 to 50 meters, could still cause significant local damage. Think the Chelyabinsk event in Russia in 2013, which was caused by an object estimated to be about 20 meters across and wasn't detected until it was already entering the atmosphere. While these smaller events are more common, they typically don't pose a global threat. However, continuous improvement in detection capabilities and developing more rapid response systems for short warning events remains an active area of research and development. It's a constant race against the vastness and unpredictability of space.
The Chelyabinsk event is a stark reminder that even smaller objects can have a significant impact, both literally and figuratively. It highlights the need for not only early detection of large objects, but also improved vigilance for the smaller, more frequent ones. So, what's next for the Rubin Observatory and for planetary defense in general? What are the immediate goals and the long term vision?
The immediate goal for Rubin is to ramp up to full operational capacity, which means consistently scanning the entire southern sky every few nights. The data deluge will begin in earnest, and the scientific community will be working tirelessly to process and analyze it. For planetary defense, the long-term vision is to achieve a nearly complete catalog of all potentially hazardous asteroids, especially those larger than 140 meters. This will give humanity the best possible chance to detect any future threats with enough lead time to implement deflection missions. It's also about fostering international collaboration, sharing data, and developing robust decision-making frameworks for when or if a real threat is identified. It's a multi-generational effort to ensure the long-term safety of our planet, building on the incredible technological advancements we're seeing today.
It's truly incredible to think about the scope of this endeavor. From a single observatory in Chile, we're gaining an unprecedented understanding of our entire solar system, identifying thousands of objects that were previously unknown, and significantly enhancing our ability to protect our planet. It's a testament to human ingenuity and our persistent drive to explore and understand the universe around us. I mean, the fact that we can even discuss the possibility of nudging an asteroid to save Earth is just mind blowing.
It really is, Alex, and it fundamentally changes our relationship with the cosmos. For so long, asteroid impacts were seen as purely random, unavoidable acts of nature. But now, with observatories like Rubin leading the charge, we're actively taking steps towards becoming guardians of our own planet. It's not about fear, it's about empowerment through knowledge. Knowing that those 11,000 new asteroids, and specifically the 33 NEOs, have been found and are being tracked is a sign of progress, not peril. It means we're doing our job of watching the skies better than ever before.
And that's a profoundly reassuring thought, Maya. It's not about being afraid of what's heading our way, but about celebrating the tools and the minds that are allowing us to see it, understand it, and prepare for it, even if that preparation is for something that hopefully never comes. The Rubin Observatory is truly a beacon of what humanity can achieve when we set our sights on the stars, not just for discovery, but for defense.
I couldn't agree more. It's a perfect example of how advancements in pure scientific research can have incredibly practical and life-saving applications. The more we know about the objects sharing our cosmic dance floor, the better equipped we are to keep Earth safe and sound. It's an exciting time to be looking up at the night sky, even if sometimes the headlines sound a little scary at first glance. We're actively writing the next chapter of planetary defense, and the Rubin Observatory is one of the biggest pens in the universe.